Hi everybody, thanks for watching this video. My name is Sebastián Montoya. I'm a master student at the Civil and Environmental Engineering Department in the University of Maine under the advice of Professors Aaron Gallan and Bill Davids. In a partnership with the Maine DOT, who provided the financial support for this project, we performed an assessment of micropile-supported integral abutment bridges. So integral abutment bridges are preferred because they have low maintenance costs, and then think on this kind of bridges um, at shallow bedrock sites. So because they are typically supported on ribbon piles, those are not longer an option when we have shallow bedrock, as we cannot penetrate rock, develop enough fixity. So an alternative is the use of micropiles. But because these elements are smaller in size and come into segmental pieces that are connected to a thread joint, they can be structurally weak and insufficient. And thus, the question is, how long can we build these bridges so that they safely perform with this kind of supporting system? So the goal of this project is to assess the structural capacity and the applicable span lengths for micropile-supported general abutment bridges. And we did want to know that for different bridge geometries and considering different subsurface conditions. So to attain that goal, we perform a parametric study model into a final element using the final element method. We use the commercial software Plaxis 3D, and in our parametric study, which is an extension of a validated model that we did reproducing experimental data. So in the parametric study, we varied the span length, we changed the bedrock depth, the soil type, we changed the skew angle of the bridge, and of course, we consider different micropile sizes going from outer diameter of 7 inches up to 13 inches. Now, what we did is to assess the demand capacity for these micropile sizes. So that's represented according to Ash provision by our parameter f, where we're showing just the interaction between axial and flexural loads. In this equation, the PU and MU are our factor axial and bending loadings, while PN and MN are our nominal axial and flexural capacity. Now, because these elements are mainly on compression, the axial capacity is taken according to Ash2 as 80% of the yielding axial load, while for the flexural capacity, well, we have to talk about now about the difference between the joint and the intact section. And with intact, I refer to a section where there's no joint. So in the intact section, we assume we can develop a plastic hinge. So the capacity there will be the plastic moment. That's just the plastic section modulus times the yielding stress. While at the joint, we have to talk about a reduced capacity. So there are very few work about this into the literature. One of the few you can find is the FHWA reference manual. Well, they just propose that a simplified approach would be to reduce the thickness of the pipe to 50%. To consider the reduced capacity of the joint, and that yield, that the flexural capacity of the joint is just 50% of the yielding moment. That is just this elastic section modulus times the yielding stress. Now, any value of F equal to 1 means that our demand exceeds our combined capacity, and that's what it should be avoided. Our results are summarized into figure 3 and 4. Now, figure 3 is showing our interaction diagrams where we have in the vertical axis our axial load demand normalized by our capacity, and in the horizontal axis we have the bending load demand normalized by the bending capacity. In figures A, B, C, and D, we're just talking about different subsurface conditions, going from the top figures for sandy soils to the bottom figures for clayey soils. And the figures in the left, AC refers to shallow bedrock depth. That means just 5 feet of thickness below the abutment. And in the right figures, we have the deeper bedrock depths. 15 feet. Now, we choose these values because 5 is the practical limit of the shallow bedrock depth using this kind of foundation system. And 15, beyond 15 for these micropile types. Beyond that, you will already reach the fixed depth. So it will make no substantial difference going deeper than that. And now we assess the demand right at the head of the pile because this one has the greatest axial and bending loads. So that means that if we satisfy demand at the top, we will be okay for the lining of the depth. Now, the markers have different symbols. The symbols represent each one of the 5 sides, while they have different colors that represent the different span lengths we're assessing. So we have essentially here all the permutations we perform in our study for just the non-skewed bridges. Now, something interesting that arises just from observation of this figure is that if for deeper bedrock depths provide a more convenient scenario for the structural demand of the micropiles. We know that because, for instance, for sandy soils, the markers that represent our data points are far from the interaction line. That means they provide less demand. And that gets more evident for clay soil when we know that many points that were before outside of our interaction diagram, that means failure, are many of them now just at the line or below them, meaning that conditions that were unacceptable before for shallow bedrock depth are now acceptable for deep bedrocks. If we consider all the data points and we could establish, well, we may note that most of the points that are outside of the diagram belongs to the span length of 150 feet. So we can establish a practical limit here about 125 feet or 100 feet, depending on our soil conditions and the pile size we are talking about. Now, that's for the intact gross section. But what about the joint? Well, when it comes about the joint, we cannot perform the same analysis we did here because we need to assess the interaction equation at the location of the joint. But that's not a priori. That's something that could be controlled during the design process or can vary during the construction process. So what we really need is to assess this interaction equation at every single depth and then identify the depths at which our joint will not perform safely. And that's what we summarize into figure 4. Now in figure 4, we have depth in the vertical axis, left for standardized normalized depth or relative depth to the bedrock depth. And in the right, we have our real depth. Right? Now in the top figures, again, we A, B, C, and D represent our difference of surface conditions. And what we show in the horizontal axis are our different span lengths. So for any span length, we set F value, and we identify different zones. A green zone on which all the micropiles with presented values of F less than 1, a yellow zone in which all the micropile types show a value of F greater than 1 or in at least one pile type shown, and a red zone in which all of the pipes presented failure. So in this case, for a given span length, you should avoid red, and probably you can deal with yellow zone, but the more convenient is to locate your joint into the green zone. Again, we know in this case, bedrock depths, increasing bedrock depths now provide a more detrimental scenario. That's because we are allowing loads to dissipate all through the depth, so that increase the loads at deeper locations. while stiffer soils are more convenient because those dissipate loads more easily. In summary, if we talk about the development of the plastic hinge, our bridge length will be limited to 100 or to 125 feet. But if we talk about the joint capacity and the performance of the joint, that could be even shorter, down to 75 feet, depending on our soil condition, or we can reach 150 feet if our conditions are favorable. Thank you so much for watching this presentation. I hope you have any question and I will be glad to answer them.